So good afternoon, good morning, ladies and gents. Very good to see you. Welcome to the SAD class exam 2 preparation. This is going to be uploaded to Blackboard on Friday afternoon or thereabouts. What we have here is the supporting slides and me talking over those slides that I released on Friday morning. Okay, so shall we just crack on and go through it? I hope you dig my my background. I have a green screen. It's very cool. So you can see I have a green screen and I have different pictures up there. I was going to have lots of pictures of various professors, but I thought the Cougars playing football is probably best. Right, let's go for it. So data flow diagrams depicts the movement of data between external entities and the processes and the data stores within them. You'll remember the symbols, I hope. So we're interested in the gain and Sarsen symbols on the right-hand side. So we have a process, this curved square with a colored in top where we're going to have our information telling us just by a glance of what level of diagram we are at. We have data stores where our data is stored while it's not being moved. We have this square rectangle, this source of the sink. The source is the source of the data external to our system, and the sink is another area external to our system where our data flows to once it leaves our information system. And then we have our data flow there with our arrows. So the very highest level of data flow diagram is what we call the context diagram. You'll note, we know it's a context diagram for two reasons. A, it only contains one process, which has a label of 0, and B, it has no data stores, okay? So you can see straight away that the fact that we have a 0, one process, and no data stores, this is the context diagram. Okay, so what do we have here? Customer is a source and a sink, kitchen is a sink, and restaurant manager is a sink. Now you will recall that to traverse to lower level diagrams of our data flow diagrams, we go up and down through the processes. So here we have our food ordering system process. So to go down to the next level of detail, we would go down through our process, the food ordering system process, and we would see this. Now, this is called the level 0 diagram. It's the highest level diagram underneath the context level diagram. You can see we're now seeing multiple processes. We've still got our original sources and sinks. We're also now seeing data stores. We're seeing data flow within the multiple processes and the data stores. So we're seeing a higher level of detail. The processes, we know at the level of 0. How do we know we're at the level 0 diagram? If we look at the labeling for the processes, we can see 1.0, 2.0, 3.0, and so on and so forth. That tells us, so we're not at the very highest level, because that would be a level 0. The fact we've got 1.0 tells us we're at the level diagram. So 2.0, 3.0, and so on and so forth. And again, to go down to the level 1 level, we would go down through each of the processes. So for each process, I can just keep on going down and down and down and down. So I can go to as many details of levels of detail I can as in the 1.0 process, the 2.0 process, the 3.0 process, and so on and so forth. Okay. Here are some of the rules. Just let me move my picture of me out of the way. Okay, so do remember that if I have a process and I have data flow coming out of my process, there has to be data flow going into it. If it was only coming out of it, it would be a source, but it's not as a process. That's number A. Number B, for me to have only data coming into it, it would be a sink, but we have a process here, so we need to have data coming in and going out. You will recall we cannot have data flows between data store directly to data store. This is part D. We need to have a process in the way. I've just realized there's no C. A, B, D, E, F. Oh, well, there you go. So data store to data store we can't do. We have to have a process in the middle. Similarly, we can't have a source to a data store. We need to have a process in the middle. And similarly, we can't have a data source directly to a sink. We need to have a process in the middle. Let's see some more. What more do we have? Oops. There we go. We can't have source directly to sink. The reason why we wouldn't have source directly to sink, because that's all external to the system. Now, it may well be the case that this is a fine, good, no problem data flow, but it's not relevant to our system unless it is going via a process in our system. So if there is no process between the source and the sink, it's of no interest to us. You can't have a bidirectional data flow from a process to a data store and back again. You've got to have two distinct flows of data. So per J, you don't have a bidirectional arrow, you have different data flows. Per K, you can see we have data flow going from one process to two further processes, but you'll notice that data flow A, you can't branch off and have a different data flow B going to a different process. You can have that happening, but it has to be the same data that is branching off. Similarly, you can't have different data flows merging to go to a process or any other outcome. You can only have the same data coming from different areas, different processes, merging and then going on to wherever they need to go on to. And per M, you can't have a data flow leave a process and then come straight back into it without it touching any other process or data store or whatever. As you can see on the right-hand side, if it leaves a data flow, if the data flow leaves a process, it has to go to another process and then back again. Okay, so we have to have an external interaction for that to come back. Very good. Decomposition. Functional decomposition. We all talk about decomposition and denormalization and all that good stuff. Got to remember that decomposition, this is the iterative process of breaking a system description down into finer and finer detail. So as we move down beneath each level process, going down to finer levels of details, we can come up with an awful lot of details, all right? Just remember, the lowest level that we can go to is what we call the primitive data flow diagram. Okay, so level 1 diagram results from decomposition of level 0 diagram, level 2 from level 1, level 3 from level 2, and so on and so forth. And level n, therefore, is the data flow diagram that's a result of n nested decompositions from a process on a level 0 diagram. Typically, we get down to about, rule of thumb, 7 processes there or thereabouts. Okay. Now remember as well that as we decompose our data flow diagrams and we're going down to a finer level of detail, okay, we need to have a balanced data flow diagram. We need to keep our sources and our sinks the same. If I go back up, you'll see here our sources and sinks are customer, kitchen, and restaurant manager. As I decompose from the context diagram down to a level 0, I still have my customer, kitchen, and restaurant manager sources and sinks. I'm balancing my data flow diagrams, and this is what this is all about. So the example they give here, you can see in the top one we have one source and one sink, yet when we decompose this context level diagram down to level 0, suddenly we have a source 2 that comes into our 1.0 process. That source 2 should have been captured at our context level diagram above. The fact that it's not means that there is something wrong. Very good. We can also split data. So you can see here, what does it say? Data flow splitting. A composite data flow at a higher level is split and different parts go to different processes in the lower level DFD. It's still balanced because the same data is involved, should be same data are involved, but split into 2 parts. So here we can have payment and coupon at, let's say, level 0. And if we take that process down to level 1, we can have that payment and coupon data flow split out. So you remember as well, so we can also use data flow diagrams as analysis tools. And one of the analysis tools we might be using, or context, would be doing a gap analysis. This process of discovering discrepancies between 2 or more sets of DFDs or within a single data flow diagram. Do you remember that example we talked about where those IBM managers came in and they had a look at the flow of data and went from a very high manual overhead process where it took something like 6 days to get a sales quote in dealt with and out again, and they got it down to 15 minutes. So that example is a very good reason why we might want to use a data flow diagram to do our gap analysis. Do go back and have a look at that chapter. I think it's chapter 7a, where we went through that example, because that will really help you kind of cement it up here. Okay, very good. We also went through this thing of modeling logic with decision tables. Hopefully you remember this. You'll remember that what we're trying to do in this example, this is a payroll information system, and we're trying to work out what actions the information systems takes depending on the conditions, the actions, and the rules. So what is our definitions? Condition stubs, the conditions relevant to a decision. Action stubs, the actions that result for a set of conditions, and then the rules, which actions are to be followed for a set of conditions. Okay, so let's have a look-see. Oh, I've jumped ahead of myself. Okay, so here we have our condition stubs. We have our employee type, whether we're an S, a salaried employee, or H, an hourly employee. We have the hours worked, less than 40, exactly 40, or more than 40. We have our action stubs. So depending on the conditions and the rules, we will do the following actions. We'll either pay the base salary or calculate hourly wage or calculate overtime or produce absence reports. So we saw that if you're salaried, you work less than 40, the action is to pay your base salary. If you're if you're an hourly employee and you work less than 40, you'll calculate your hourly wage and produce an absence report, and so on and so forth. Okay, so I think this was pretty self-explanatory. But then we realized as well that we can actually reduce this decision table, right? We can make it almost like more efficient. We call this an indifferent condition, okay? So a condition whose value does not affect which actions are taken for 2 or more rules. So we know that salaried employees, irrespective of the hours that they work, they get paid their base salary. So we can go from this larger decision table where we have redundant data to a more refined or reduced decision table where we are only demonstrating the actions, the rules, and the conditions that are necessary for our information system. Okay, very good. Let's move on. Use cases, depiction of a system's behavior or functionality under various conditions as the system responds to requests from users. Okay, let's have a look at this. Ah, yes, I remember this. So this is a use case diagram which depicts system behavior along with the key actors that interact with the system. So there we have an example, student as an actor. What is an actor? And this external entity that interacts with the system. It's not a specific person. I'm not talking about a specific student. I'm talking about this conceptual role, this group of students, you guys as students, okay? What else do we have? Where it says Bill student, these round circles, this is a use case. What's a use case? Depiction of a system's behavior or functionality under various conditions as the system responds to requests from users. Okay. We also have this thing called an abstract use case, a type of use case that is initiated by another use case instead of by an actor. And we have 2 here, register for special class and identify prerequisite courses not complete. We'll get to those in a little while. So this is a use case diagram for a university registration system. Okay, so you'll recall this is how an information system interacts with with actors, and what the information system does as a result. So we have actors as a bursar's office, student, registration clerk, and instructor. So the bursar's office places the order or initiates the behavior or functionality to bill student. And so the bill student use case interacts with the actor, the student. The student interacts with the use case register for classes, as does the registration class, and so on and so forth. So we have actor and use case. What else do we have? We have connection and system boundary. What is system boundary? System boundary is just that boundary around the information system to demonstrate which use cases are potentially occurring or are occurring within that information system. Okay, so use cases inside, actors outside. And then a connection is just a relationship between an actor and a use case. Does not indicate data flow. You won't see any arrows, okay? You only see arrows with use cases connected with another use case, okay? So I don't think there's anything too scary with all of that. So you'll notice here we have an extend relationship between register for special class and register for classes. What's an extend relationship? An extend relationship is an association between two use cases where one adds new behaviors or actions to the other. So normally you would do only the actions that are in register for classes. But in special situations when you have to add in extra actions, then those extra actions to be added on will be, in this example, stored within the use case register for special class. So it's an extension of a pre-existing level of actions. An include relationship, an association between two use cases where one uses the functionality contained in the other. So do you remember that example we had where we were a shop owner and we wanted to place an order? At the same time as we place an order, we also initiate a reporting tool use case, so that as and when we do something, we also use the functionality in another use case at the same time. So at the same time that I'm placing an order, I'm also using the functionality to generate a report of what I'm ordering and also send an update to my manager. So include relationship essentially is what I'm saying is when I include another use case and an include relationship, I'm using the functionality in the other use case at the same time as what I'm doing in my original use case. Okay, good stuff. Yes, now level refers to the degree of detail in the use case description. We can either go from a very high level, very summary level, white, down to a very detailed level, black. Just remember the levels: white, kite, blue, fish, and black. Okay, moving swiftly on. Activity diagrams shows the conditional logic for the sequence of system activities needed to accomplish a business problem. Yes, do you remember this? So we had all these different diagrams, different, I'm having a blank. So I forgot the word for symbols. Oh my goodness, it's been a long day. All right, so we have many symbols in our activity diagrams. So we first of all see we have 4 swim lanes: purchasing, fulfillment, customer service, and accounting. A swim lane, columns representing different organizational units of the system, these vertical lines. We have our start there at the very top underneath customer service, the beginning of a process, a filled in circle. We have an activity, this rectangle, behavior that an object carries out while in a particular state. So we have receive order. Under receive order, we have a fork, the beginning of parallel activities, this horizontal line with 2 arrows coming out of it. We then have underneath pull available inventory in the fulfillment swim lane, this symbol branch, a condition whose results provide transitions to different activity paths. And this diamond, either we go one way or we go another way. It's not going in parallel, it's a branch out and making a decision, okay? When we come to the end of a branching out, we have a merge. I can't even say it. Where different paths converge. Again, a diamond, the difference being the arrows are pointing inwards. At the end of parallel activities that were initiated with a fork, we have a join, where we have this horizontal line with 2 arrows coming into it. And then the end of a process is a filled in circle that has another circle around it. I don't think there's too many things we have to worry about on that. I think you're pretty cool with that. Sequence diagrams used to show interactions amongst objects for a particular use case. Just remember what we have here. We have from the top of the diagram to the bottom. The top is earlier in time. The bottom of the diagram is later in time. Objects, which are represented by the box at the top of the diagrams. These are objects, things that happen, things that interact with other objects. The lifeline is the time during which an object exists. An activation is the time period during which an object performs an operation. And then the message is the means by which objects communicate with each other. If you remember back to the class, you'll recall you're given the opportunity to go away and work on some of these sequence diagrams yourself to get a really good understanding of them. Now you recall as well, we had different types of messages. You can have synchronous messages, simple messages, and asynchronous messages. Synchronous message, what's it say? Call has to wait for the receiving object to finish executing the called operation before it can resume execution itself. A simple message transfers control from the sender to the recipient without describing the details of the communication. And then an asynchronous message, the sender does not have to wait for the recipient to handle the message. So just remember the differences between those. It's important, if you look here, we have examples of synchronous and asynchronous and simple. It all depends on the nature of the interaction between the objects. Okay, very good. BPM, business process modeling, modeling the standard methods for accomplishing a particular task necessary for an organization to function. Let's look at the symbols. We have event, this trigger that initiates the start of a process, activity, action that must take place for a process to be completed, gateway, our decision point, and our flow shows a sequence of action in a process. We also had these specialized notation. Do you remember your assignments where you had to go to the bpn.org website and find 5 different specialized notations and share those and explain them for your assignment? Okay, so hopefully you have a good understanding about what is meant by specialized notation. Here we have an event notation that starts either by a message or at a particular time. We also have examples here of different flow notations, i.e. a normal sequence or a default flow, where in the absence of other information, you would have a default version or direction that you would take, or a flow that begins with a message. Very good. We also had different types of gateways. We have XOR, and OR. You can read them about here. And here we had our example that we walked through in class. So we had 2 swim lanes in company and an applicant swim lane as well, where we had 2 swim lanes within a single organization. That was called a pool. And if you start top left with the manager with our event, and then you can go to activities and the data flows, and you can see the interactions, and you work through going up and down and from left to right and so on and so forth. I don't think there's anything too complicated with that, and I think you'll be fine if you get asked any questions on that. And then we go into entity relationship modeling, the detailed logical relationship of representation of the entities, associations, and data elements for an organization or business area. Do you remember the terminology? I gave you this screen just to, the slide, just to make sure you understand the difference between what we talk about, an example of what we talked about, and what we would actually call it in this world, in the entity world. So we had object type becomes entity type, object instance becomes entity instance, object class, entity class, property attribute, fact value, property value set domain, and association relationship. And we looked at the example of horses. You remember that horse entity type, and it was all great. Right, so what are the elements? We have an ER model and an ER diagram. So an ER model, this detailed logical representation of the entities, associations, and data elements for an organization or business area. So we're interested in data entities, relationships, and attributes. And then in support, we have an ER diagram, which is this graphical representation of the ER model. So we have a really deep understanding of it. So let's go through this in detail. So if you've done the database class already, or you're doing it, you're obviously going to be ahead of the curve, because this is all the stuff you talk about in database class as well. So an entity, a person, place, an object, event, or concept in the user environment about which the organization wishes to maintain data. So examples might be employee, product, registration, account, course, warehouse. Again, these are all nouns, as you will see. So an entity type, we call an entity at the same time. They're kind of used interactively, not interactive, what's the word I'm looking for? You can use either. Essentially, we should call them entity type, everybody just calls them entities. This is a collection of entities that share common property or characteristics. Okay, so we will look at that. The horse type, entity type, had lots of horse entities within it. So an entity instance is a single occurrence of an entity type. Very good. So it's a singular noun, it's a noun, it's a student, not students, it's descriptive and specific to the organization, and it is concise. So how do you define entity types? You include a statement of the unique characteristics. You clarify what entity instances are included and not included. You include a description of when an instance of the entity type is created and deleted. Some definitions must specify when an instance might change into an instance of another entity type, and so on and so forth. Attributes. Attributes, this property or characteristic of an entity that is of interest to the organization. So you might see employee ID or employee name or payroll address or skill in the employee entity on the right-hand side. So these again should be nouns. They must be unique, not just within the single entity, but across all the different entity types going on. Okay, and again, we have guidelines for defining attributes, and you can read those yourself, no problem. Do you remember this? So this is the example of the horse entity. So we had an entity type of horse, our attributes, name, color, spots, gender, weight. Our entity instances with the individual rows of each horse. We had the values in each cell where entity instance crosses with an attribute. So Joan is a value, as is Brown, as is No, as is female, as is 1250, and so on and so forth. We have entity class. In this example, it could be horse. Those attributes could be used to describe any animal. And then relationships. Do you remember we may have had relationships between horse and stable and owner, and those would be in different entity types. And in that case, we would be able to start thinking about the relationships between a given horse, a given stable, and a given owner. And we also had our domains, this property value set, where we define what values you are allowed to enter into your entity. So in spots, you can only put no or yes. In gender, you can only put F or M. In weight, you can only put in a value between 800 and 2200, and so on and so forth. I think we discussed this a lot in class, and I think you have a pretty good understanding all about that. Now then, candidate keys. So candidate keys, remember, an attribute or a combination of attributes that uniquely identifies each instance of an entity type. And you remember, you can have multiple candidate keys. Some entities may have indeed multiple candidate keys. Of these candidate keys, if you have more than one, you need to select one as the unique identifying characteristic for an entity type. And in the entity world, this is called an identifier. When we get to relations, we start talking about primary keys, exactly the same thing. Okay, so you can have multiple candidate keys in your entity type, but one we're going to choose as our identifier. It's the same thing as a primary keys, and we recognize that by drawing a horizontal line underneath it. In this example, employee ID is our unique identifier. Okay, you want to have one where it's not going to change its value ever. And remember, with our unique identifiers and with primary keys later on in our relations, we do not allow null values. Remember that a null value is not a value of 0. A null value is the absence of a value. We can, at this early stage as well, allow multi-valued attributes as well. So you can have more than one value for each entity instance. So here, for instance, let's say Sam was brown and white. I would allow brown, white in the value for the color attribute. And at this stage, I'm allowing you to do that. Now, as we get closer to our final end game, and then we move to relations and so on and so forth, and we move to logical and then into physical, we do not allow multi-values. But at this stage, we are allowing that to happen. We can capture multi-valued attributes in entity types. At this stage, we have these cedillas, these curly braces or brackets around them. So here you can see skill has that, makes you know it's a multi-valued attribute. What else do we have? Required attribute, an attribute that must have a value for every entity instance. It's got bold text. An optional attribute that does not, it's an attribute that does not have to have a value for every entity, normal text. A composite attribute that has meaningful component parts, such as address, which is made up of street, city, state, and zip. And then a derived attribute whose value can be computed from related attribute values, i.e., you know that I'm 31 because I was born in
1979, 89, 80. Oh, you know what I'm saying. All right, you can work it out from another attribute. Very good. And relationships. Naming and defining relationships. A relationship name is a descriptive verb phrase. We avoid vague names, e.g. assigned to, not assignment. So definition of relationship explains what actions to be taken and possibly why it's important, and gives examples to clarify the action. Now we have different degrees of relationships. Do you remember, if we have a relationship between two entity types, that's a binary relationship. If we have a relationship between the instances of only one entity type, that's a unary relationship. And if there's three, it's ternary, quaternary is for four, quinternary is 5, and so on and so forth. So degree, the number of entity types that participate in a relationship. The thing to remember about relationships, it's not a relationship per se, and this is my bad, because the way I talk about it, I talk about a relationship between one entity type and another entity type. And it's not actually. It's a relationship between an instance in one entity type and an instance in another entity type, or an instance in one entity type with another instance in that one entity type. Okay, so it's a relationship between instances. Okay, these are either located in the same entity type or in different entity types. Very good. Cardinality, the number of entity instances associated with another entity. So we have optional participation, where our minimum cardinality is 0. If I have a minimum cardinality of 0, do I have to be participating in whatever it is? No. The minimum I have is 0. If I have a minimum score of 0, I do not have to have participate. A mandatory participation is where the minimum cardinality is greater than 0. So maybe 1, it could be more than 1. A many is where a maximum cardinality is more than 1. And we can also have a fixed number as well. So a maximum cardinality of, let's say, fixed number n, a maximum cardinality is n. So you remember, we have our crow's feet notation. So a mandatory one, where we have a minimum of 1 and a maximum 1, we're talking about 1, okay? A minimum of 1 and a maximum of many, it's a mandatory many. So a minimum of 1 and a maximum of many, I have to participate because I've got a minimum of 1, but it could be many, whatever it is, the context of what I'm participating in. An optional one, where the minimum cardinality is 0 and a maximum is 1. And then an optional many, a minimum cardinality is 0 and a maximum of many. So Professor Skinner teaches 0 to 1 classes. This is optional participation with a maximum cardinality of 1, i.e. optional 1. Professor Skinner teaches a minimum of 0 classes and a maximum of 1 class. If I'm teaching 0 classes, I don't have to teach a class. All right, that's basically what it means by optional participation. If I say SAD is taught by 1 to many professors, mandatory participation with a maximum cardinality of many, mandatory many. For a class to be taught, or SAD to be taught, you need at least 1 professor, okay? So it's not optional, you need to have at least 1. It's mandatory for this class to be taught, it needs to have a professor. So SAD is taught by a minimum of 1 professor and by a maximum of many professors. Yes, and here we had some examples. Let me just move this out of the way. So we had here, if you look at the top example, we had some mandatory cardinalities. So a patient has recorded a minimum of 1 patient history and a maximum of many patient histories. A patient history is recorded for a minimum of 1 patient and a maximum of 1 patient. So a patient history is assigned just to 1 patient, and we can see that on the right hand side for Mark, Sarah, and Elsie. We can also see for the next one down, our optional and 1 mandatory cardinality. An employee is assigned to a minimum of 0 and to a maximum of many projects. So an employee is either working on no projects at all, or at the very maximum, they're working on more than 1 project. A project is always assigned to a minimum of 1 employee and a maximum of many employees. So a project is always assigned to at least 1 employee, but it can be assigned to many. So in this example, we have mandatory cardinality between project and employee. And again, we can see that on the right-hand side for Rose, Pete, Debbie, Tom, and Heidi, and for the BPR, TQM, OO, and CR projects. We can see in the bottom example, in optional cardinalities, we have a unary relationship, also known as a recursive relationship, where a person is married to a minimum of 0 and to a maximum of 1, unless they live in Utah, and the same going back. So you're either married to no one or you're married to no more than one person. Very good. I think you got this in the class. So just remember, we have some of our symbols here. We have strong and weak. We talked about weak entity types. Remember, a weak entity type is an entity type. Let me just go ahead and look at my notes to see if we talk about that in this class. Yes, we do, so I won't talk about that now. I don't think there's anything here that is of any concern. Attributes, look at the attributes. Again, I'm not too worried about these different rules for attributes, and you won't be asked about the different things for optional, derived, multi-valued, or composite, or partial identifiers in the exam. Interestingly, we don't actually talk about this in the database class either. This is just an SAD thing, so don't worry about it from an exam perspective. But you may be asked questions on relationship degrees. You will certainly be asked questions about relationship cardinalities when it comes to the exam next week. So we have strong and weak entities. A strong entity always exists. Professor Skinner always exists. The subject, SAD, always exists. A weak entity only exists when based on a strong entity. So the course, MIS 3360, section 1 of 3, only exists when a subject is taught by a professor. And we represent this weak entity with a double box around it. So here we had another useful screen for you, which I recommend you practice on. Make sure you understand it, move around, make sure, buddy up with people. Practice making sure you understand what each interaction, what each relationship is all about. You'll notice as well, just under supplier, we have the number 4 there. We're actually able to define the maximum number, or the number we are referring to when we refer to many. So just be aware of that as well. Very good. Yes, now supertypes and subtypes. A supertype, a generic entity type that has a relationship with one or more subtypes. A subtype, a subgrouping of entities in an entity type, which is meaningful to the organization and shares common attributes or relationships distinct from other subgroupings. I'm just going to have a quick drink. Thank you very much. So here we have an example. So let's just do the relationship between the patient entity type and the responsible physician entity type. So we see that patient is cared for by a minimum of 1 and a maximum of 1 responsible physician. So a patient is assigned to 1 physician. A physician cares for a minimum of 0 patients and a maximum of many patients. So a responsible physician is either assigned to no patients at all or a maximum of many patients. Nothing crazy there. We can see that patient has 3 attributes: patient ID, patient name, and admit date. So patient ID is our unique identifier. We can identify each row within our entity type using our patient ID. We therefore know that patient ID does not allow null values. For responsible physician, we can see that our attribute physician ID is our only attribute, and therefore that is our unique identifier. So we can see here that patient has 2 subtypes: outpatient and resident patient. Okay, so outpatient, we have check back date attribute and date discharge. So outpatient and resident patient will use the patient ID primary or unique identifier, the patient name attribute, and the admit date attribute, as well as each of their own check back date and date discharged attributes. Okay, so that circle with the 2 lines coming off, that is telling us that we are here in a relationship between a supertype and a subtype. And just because we're a subtype doesn't mean that we too can't have relationships with other entity types. So here we can see that resident patient has a relationship with bed. So a resident patient is assigned to a minimum of 1 and a maximum of 1 beds. So one patient to 1 bed. And a bed is assigned to a minimum of 0 and to a maximum of 1 patient. So a bed is either assigned to a patient or it's not. Oh yes, types, blah, blah. Good. Business rules. Business rules, specifications that preserve the integrity of the logical data model, captured during requires determination. Good stuff. Ah, here we go. Yes, yes, yes. Let me get to my notes. So what do we have? 4 business rules that we want to capture. Total specialization, partial specialization, disjoint rule, and overlap rule. Let's look at these in turn. So total specialization, this double line, each entity instance of the supertype must be a member of some subtype in the relationship. Excuse me. So if you're a person, you are either an employee, an alumnus, or a student in the context of this relationship between these entity types if it's for a university. Okay. Partial specialization, this single line, an entity instance of the supertype does not have to belong to any subtype and may or may not be an instance of one of the subtypes. So if you're an employee, if you're faculty and staff, if you're an employee, you may not be. What's a teaching assistant? The teaching assistant gets paid by the university, but it's not faculty, it's not staff. So that's a partial specialization. Overlap, an entity instance can simultaneously be a member of 2 or more subtypes. So if you are a student or an alumnus, or you can be both at the same time, or an employee. I'm actually one of this. So I'm an employee, I'm faculty, and I'm an alumnus. I did my PhD at the University of Houston. So this is where it comes into play. And then the disjoint, if an entity instance of the supertype is a member of one subtype, it cannot simultaneously be a member of any other subtype. So you're either a graduate student or an undergraduate student. You can't be both in this example. I don't think there's anything there which is too concerning. So we have different types of business rules. We have the entity integrity business rule, which says we have to have unique non-null identifiers. We've already talked about that. We have referential integrity constraints, these rules governing the relationships between entity types. And we'll get to that in due course when we talk about things like foreign keys and so on and so forth down the line when you get to relations. Domains, constraint on the valid values for attributes. We've already talked about this. We've already talked about how we can define what values in our property value set you are going to allow. And then we have the triggering operations. And we can talk, do you remember we gave that example about trying to take money out of account? We'll get to that slide very shortly. You can talk through that as well. So our triggering operations, these other business rules that protect the validity of attribute values. So just to remind us about domains, set of all data types and values that an attribute can assume. The advantages, well, we can verify that the values are attribute are valid, make sure that all our operations make sense or are logical, helps conserve effort in describing attribute characteristics. The reason why I found in real life that having domains in place was so useful, it's easier to support, right? It's less overhead, it's less manual work that you need to do to make sure that all the values that you are putting in make sense. Triggering operations. So triggering operations, these rules that govern the validity of data manipulation operations, such as insert, update, and delete. Do you remember in that class where we talked about SQL, the structured query language? And this is our way of manipulating our data. So maybe we might use the insert command to insert new data into our database. If we have existing data in there already and we want to make changes to it, maybe we'd do an update. So we'd update data to be a new value from what it was before. Or maybe we want to get rid of the data and we would do so by deleting it. These are all manipulation operations of our data in our database. So we need to control these in such a way that if somebody tries to do something to the data and we don't want that thing to happen, we can put rules and parameters or boundaries around what manipulations are allowable under what situations. Okay, so what are the component parts of our trigger? We have here, they are 5 of them. This user rule, this event, the entity name, the condition, and the action. Do you remember in class we went through each of these? And we had this example. Should we just walk through it very quickly to make sure we understand it? I think so. So we have 2 entity types, account and withdrawal. We have account with attributes account number and balance, and we have withdrawal with our attributes of date and time and amount. Okay, so an account is for a minimum of 0 and a maximum of many withdrawals. A withdrawal is for a minimum of 1 account or maximum 1 account, so for 1 account. Okay, we have, let's look at our domain, our property value sets for 2 attributes. In account, let's look at our attribute account number. So we have a meaning, this is our customer account number in our bank. A data type is character, we have a format. Unique has to be unique, where's our unique identifier, and null support non-null. We do not allow null values. If we look at amounts in our withdrawal entity type, we can see that this is a numeric, format 2 decimal places, a range up to 10,000. So every time we want to take out any money, we can only take up to a maximum of $10,000. That'll be the day. We allow multiple, the same amount of money to be taken out. We'd say non-unique. We wouldn't have this as unique, remember, because if I tried to take out $100 once, and if it was a unique value, I'd never be allowed to take out exactly $100 ever again. So it's fine, that makes sense. And again, we don't allow null values. So essentially the relationship between these 2 entity types, what we're saying is that each time we try to withdraw, make a withdrawal from our account, from the account number of whatever it is, we can only take out the amount of money that we can that is based on our balance number, our balance value in the account entity type. Okay, so let's see what how I can say that. Let's look at our triggering operation, which basically is all of these components. So our user rule, withdrawal entity type amounts, the value in the amount attribute, may not exceed account entity type balance attribute value. So if I try to take amount, if I put, let's say I have $5,000 in as the value in my account entity type balance attribute cell for my account number. If I have $5,000 in there and I try and do a withdrawal of 5,001 and I put that in amount, I am going to stop that going through successfully. Okay, so event insert. Now, do remember, we were a bit confused about this in the class. Insert is not inserting money. I'm trying to take out money. You've got to remember that when I'm doing an insert, I'm talking about a data insertion into my database. A data insert is essentially just recording a log, isn't it? So each time I try and do a withdrawal, I capture the date of the withdrawal, the time of withdrawal, and the amount of the withdrawal. That's the insert. Each time I do a withdrawal, I'm inserting a new entity instance of my attempt to withdraw data. So an event, in this case, refers to an insert of a new entity instance, which reflects our attempt to try to withdraw money. So the entity name is withdrawal. That's the name of our entity type. Our condition, where withdrawal amounts, withdrawal entity type, amount attribute value is greater than the account entity type balance attribute value for my account number. In that situation, I am going to reject the insert transaction. So you can see I am governing the validity. I am not going to allow things to happen that I am not going to allow to happen. And this is one of the ways that I would do it. Kind of makes sense. Okay, good stuff. Let's move on. We're about halfway through. Okay, object modeling class diagrams. What's an object? This entity with a well-defined role in an application domain with state, behavior, and identity characteristics. Okay, this is a single occurrence of a class. Bear with me 1 second. So we have object class, a logical grouping of objects that have the same or similar attributes, relationships, and behaviors, and a class diagram. So do you remember we had our object class here of students? We have our attributes of name, date of birth, year, address, and phone. It's very similar to what we've just seen in the entity world, right? But then what is slightly different is our operations that we can assign to a given object class. And here we have calc age. You'll remember there, the empty brackets means that we're referring to this object class. We're not referring to a different object class. And these are operations that we can run whether it's being for a relationship between an object in one object class with an object in another object class, or whether it's within between two objects or multiple objects within a single object class. We have different types of operations. So we have calc age, calc GPA, and register for course. These are some examples. What are the different types? A constructor. So a constructor operation for an object class creates a new instance of a class. Okay, so for instance, create student brackets, creates a new instance of student and initializes its state. We know this is going on within a single object class because of those empty brackets. A query accesses the state of an object but does not change it. So for instance, calc dash age bracket will calculate the average age of all the objects within an object class. So the average age of a student within the object class student. And then an update alters the state of an object. So I can either create, I can query, or I can update an existing object. So for instance, promote student would change the student's object state, and the value of the year, for instance, attribute would increase from, I don't know, sophomore to junior. Okay, so we have constructor, query, and update. Within the object class world, we have very similar rules to our cardinality seen within our entity type world, but slightly different versions. So multiplicity in this world, cardinality in the other. So multiplicity indicates how many objects participate in a given relationship. So instead of doing a minimum of 0 and a maximum of many, we would have 0.10 means a minimum of 0 and a maximum of 10. 1, 2 means either 1 or 2. A star means an infinite upper bound, squillions, Brazilians, millions. So it's very similar, analogous to cardinality in our entity relationship diagrams. And there you have the example there. And again, if you have a good solid understanding of cardinality, then you should be able to pick this one up very quickly as well. Yes, now then, let's look here. So we have a generalization implemented via superclass and subclasses. Look at your notes, which is analogous to supertypes and subtypes in ER diagrams. We can have overlapping, disjoint, complete, or incomplete. Overlapping, descendant may be from more than one of the subclasses. Disjoint, descendant may not be from more than one subclass. Complete, all subclasses have been specified, or incomplete, there are some additional subclasses that are not being shown in the model. If you go back to the slides in the class, we have some examples and diagrams there where we explain it. We also have abstract and concrete classes. Now this is very important. There may well be a question on this in the exam. Work through this, make sure you understand it, okay? So concrete classes that can have direct instances. Abstract classes, a class that has no direct instance, but whose descendants may have direct instances. Let me just quickly go back to, it's not an object class, but just to make sure you understand the idea, let me go back here. Here we go. So you remember, see, we have patient, and we have patient ID, patient name, and admit date. And then in outpatient, we have check back date and date discharge. For outpatient and resident patient, we're going to use all the data from patient ID, patient name, and admit date, and we're going to capture all that, as well as check back date and date discharge for both of outpatient and resident patient. Essentially, it's the same thing when we're talking about this in the object class context. So an abstract class is a class that has no direct instances, but whose descendants may have direct instances. Okay, we have abstract operation defines the form protocol of the operation, but not its implementation. And again, go and have a look at the slides and you'll make sure we understand that. We talked about it in the class. Polymorphism, we have the same operation, but they may apply to 2 or more classes in different way. Dynamic, when you see the words dynamic with those arrows, indicates an object may change subtypes, and discriminator shows which property of an object class is being abstracted. Okay, let's move on to databases. Woohoo! So logical database modeling design, through these 4 steps: develop a logical data model for each known user interface. I have to keep on stopping and recording because I'm drinking fizzy pop, and each time I have a fizzy pop, oh look, there's my green screen. Oh yeah, that's cool. Each time I have a fizzy pop, it's giving me a little bit of wind. Right, develop a logical data model, combine data requirements, translate the conceptual data model into normalized data requirements, and then compare the consolidated logical data model with the translated model. Right, so physical database design decisions. What are the decisions we're going to make? What's the data type we're going to have for each attribute, predicated on our need to minimize storage and maximize our data quality? How are we going to store? What's the structure we're going to use for storing our data? How are we organizing? How are we going to organize our files? And what media are we going to use for storage? Okay, now, yes, database design deliverables and outcomes. We've got our logical database designed, our normalized relations. Okay, so a relation, this named 2-dimensional table of data. Stop moving your laptop around, Professor Skinner. Accounts for every data element on a system input or output. So very, very similar to what we saw in the entity world, right? It looks very, very similar. We call them relations here. So a named 2-dimensional table of data. And then a physical database design is a database tables. So we've got to think about, just remember, we have the differences between an entity type, a normalized relation, and then a database table. They all look very similar, and often they do very many things, but there are subtle differences, and you have to be aware of them. So database tables results from converting our relations. It represents the coding, the definitions of the database, and we do this using our structured query language, or SQL. So at the logical database design level, we need to go through this normalization process. This process of converting complex data structures into data structures characterized by simplicity, non-redundancy, and minimal maintenance. So when we're going through all these processes of normalization, one of the reasons why we do it is we've got to get rid of redundant data. If we have data, my wife's calling, so I have just to stop because she wears the trousers. So let's move on. So what do we have? A relational database model. Right, so it represents data as a set of related tables. Okay, so relation is this named 2-dimensional table of data. So we have our columns, which are still called attributes. We have an arbitrary number of unnamed rows or records. We have our unique identifier, which we call our primary key. And again, in this example, EmpID is our attribute that we have selected as our primary key, and we then again designate that with our underline. Okay, so a shorthand notation for a relation structure. Here we can see that the name of the relation is in caps, followed by the names of the attribute in the relation. So the primary key is underlined. So customer is the name of our relation. Customer ID is the attribute that we have selected for our primary key. If you look under order, we can see that our primary key is order number. We can see that customer ID is a dotted line underneath it. That is telling us that is a foreign key. And in all honesty, I think it's probably telling us that we have either a one-to-one or a one-to-many relationship between customer and order, where we've taken the foreign key of customer, where it's a 1, and we've carried it across to order as a foreign key. But we'll get to that in due course. So our primary key, this attribute whose value is unique across all occurrences of relation. Every relation must have a primary key, which makes sure our rows are unique, and our primary key can be a single attribute, or it can be composed of multiple attributes. So remember that a primary key with multiple attributes is called a composite primary key, sorry, a composite, I'll put my teeth back in, a composite primary key, because the primary key has more than one attribute making it up. What else? What other properties of relations do we need to be aware of? So entries and cells are simple. We no longer allow multi-values that we talked about earlier on. Entries in columns are from the same set of values. In other words, all we're saying is that for attributes, we have a single domain and that the values have to conform to our domain rules. Each row is unique. Again, basically the same as we said earlier on in our entity relationship diagrams or entity modeling. Each instance, each row, each record has to be unique. The sequence of columns can be interchanged without changing the meaning, the use of the relation, and the rows may be interchanged as well, stored in any sequence. Very good. So here we go. Normalization. Normalization, the process of converting complex data structures into simple, stable data structures. I'm sure there's a joke I should be making now about horses and stables, but I'm not going to because I'm better than that. Normalization provides a stepwise approach to designing a relation that is guaranteed to be free of data redundancies using normal forms. So the whole reason why we go through this normalization process is to make sure that where we can, we get rid of redundant data, where we are having the same data in more than one location. Okay, so we know the properties of the relation. Is the first things we need to be aware of when we come to normalization, and then we need to go through this normal forms stepwise process of 1NF, 2NF, and 3NF. So let's just remind us, for a relation to be in a form of normal form, it must satisfy the following conditions. First normal form: an attribute value in a relations row must be a single value from the domain. Okay, that's fine. We don't allow multiple values for our relations at this stage. Each relation must be able to be identified by a primary key. That's fine. So we've identified a non-null attribute. My dog is barking. Let me go and shut him up. 1 second. Each row is unique, so two rows can be identical, and all the relations are in 1NF, then our environment is in first normal form. I don't think there's any problems with that. I think we all get that, and that's fine. Second normal form, the relation is in first normal form, okay, and there are no partial dependencies. Now, for each of these first normal form, second normal form, and third normal form, I've got some examples. I'm going to talk it through later on. I think I have anyway. Oh, yes, I have. Okay, so we can talk it through this in a bit more detail. So for second normal form, the relation is in first normal form and there are no partial dependencies. A partial dependency exists if the relation has a composite primary key, i.e. a primary key that is made up of more than one attribute, and if attributes in the relation depend only on part of the primary key and not the entire primary key. Okay, we'll talk about that in more detail later on. And then third normal form, for a relation to be in third normal form, the relation is already in second normal form, and there are no transitive dependencies. A transitive dependency exists when a non-primary key attribute depends on other non-primary key attributes rather than depending upon the primary key. Okay, let's work through this in a little bit more detail. So first normal form, I don't think we have any problems with it, right? An attribute value in a relations row must be a single value from the domain, fine. Must be able to be identified by a primary key, fine. Each row is unique, fine. All relations are in 1NF. Now then, for us to understand partial dependencies and transitive dependencies, we need to understand functional dependencies. So you remember from the earlier videos I gave in 9a and I think in 9b, functional dependencies specify a relationship between attributes within a relation. Let's read this together. An attribute A in a relation functionally determines another attribute B if, for a given value of A, there is a single specific value of B. So A functionally determines B if, for a given value of A, there is a single specific value of B. In other words, B is functionally dependent on A. So in this example, let's say emp ID is A and name is B. Employee ID is the unique identifier that allows each employee in an organization to be identified. So each employee will have a record or a row in our relation, right? And we're going to use unique identifier of employee ID to identify all the details of each employee, right? So let's say it another way. Our attribute employee ID functionally determines a name if for a given value of employee ID, there is a single specific value of name. So if my employee ID is 123 and the only name is Richard Skinner for employee ID 123, then we have a functional dependency. So remember, in this example, the emp ID is called the determinant. Name is our dependent. A of ant comes before E of ent, and that's how you remember it. All right, so with that all on board, the second normal form, this is based on a concept known as a full functional dependency. All right, so what does a full functional dependency mean? Each attribute that is not either a primary key or part of a primary key has to be identified by the whole of the primary key. Okay, so for a table to be in 2NF, it must be in 1NF. I can't say it. 1NF is such a difficult word to say. A relation is in 2NF if every non-prime key attribute, i.e. every attribute that is not a prime key, is fully functional dependent on the whole of the primary key. Okay, so if I have, whoops-a-daisy, if I have a relation where I have a primary key that's made up of a single attribute, I know that I'm going to be in 2NF, because to break the rule, I need to have a primary key that is made up of 2 or more attributes. So if my primary key is made up of only 1 attribute, I know I'm good. Also, if I've only got 1 attribute in the whole relation, okay, and therefore and that becomes my primary key, and therefore I've got no other attributes, again, I know I can't be breaking this rule, okay? And also, if, let me just move my thing, every non-primary key attribute is functionally dependent on the full set of primary key attributes, then again, I'm good. Let me see if we got an example. Here we go. Okay, so here's our employee-to relation. We have a composite primary key, a primary key that is made up of 2 attributes. In this example, it's emp_id and course. Okay, so going back, let's just remind ourselves, an attribute A in a relation functionally determines another attribute B if for a given value of A, there's a single specific value of B. An attribute empid and course, for a given value of empid and course, there is a given value of a dependent, then we have a functional dependency. And we have that here. So here we have empid and course functionally determines date completed. For a given value of empid and course, there is a single given value of date completed. So a value of 100 and SPSS, there is a single value of 6/19/2014. Basically, we're saying that Margaret Simpson took the course to SPSS and completed it on the 19th of June 2014. And the same for Alan Beaton, his employee ID 140 and the course tax accounting. He completed that on the 8th of December 2014, and so on and so forth. So we have no problems with empid and course functionally determining date completed. The issue arises with empid functionally determining name, department, and salary. What's our primary key? Our primary key is empid and course, those 2 attributes. But we know that empid, which is only part of our primary key, functionally determines name, department, and salary. Okay, so if with an empid of 100, we know there's a single value of Margaret Simpson, marketing, and 42,000. Okay, is empid the whole primary key or only part of the primary key? Well, empid is only part of the primary key. It's not the whole primary key. Empid is only part of empid and course. So here we have an example of a partial dependency. Empid is only part of the primary key, and it needs to be whole. So the question comes, how do we get to deal with this? Well, we decompose. We decompose our relation into two separate relations, but at the same time, we need to manage that relationship. So this first example I'm giving you is not actually the full example because we're not talking about foreign keys and so on and so forth yet. But I just want to demonstrate to you this is how we might do it. Okay, so instead of having employee 2 and our relation that is not in 2NF, to get our relations into 2NF, we would break this out from employee 2 into employee 2 and emp course. So we know that emp ID and course needs to functionally determine date completed. So we have that. So if you look at emp course relation, emp ID and course functionally determines date completed. And we have our original employee 2, what's left. We have our primary key of emp ID, and that functionally determines name, department, and salary. So we have converted our relations into 2NF, and that is all good. Third normal form, we've dealt with our partial dependencies. Now we need to deal with our transitive dependencies. So the difference between a partial dependency and a transitive dependency is not, transitive dependency is not an issue when we are only having part of the primary key as a determinant. A transitive dependency exists when an attribute that is not a A transitive dependency exists when an attribute that is not a primary key depends on other attributes that are also not primary keys rather than depending upon our primary key. You'll recall that we want our determinant to be our primary key. So here we have a relation called sales, where we have our customer ID is our primary key, and we have other attributes of customer name, salesperson, and region. What are our functional dependencies? Well, we can see that customer ID, our determinant, and our primary key functionally determines customer name, salesperson, and region. All good, no problems with that. We can also see that salesperson functionally determines region. Is salesperson our determinant in this functional determinant in our functional relation? Is salesperson a primary key? Salesperson is not a primary key. Salesperson is not a primary key, and here it is as a determinant. This is a transitive dependency. Let's look at our transitive dependency definition again. A transitive dependency exists when a non-primary key attribute depends on other non-primary key attributes rather than depending upon the primary key. Because salesperson is just a normal attribute, it's not a primary key, so we have a transitive dependency. So how do we fix this? So to convert a relation into 3NF, let's introduce the idea of a foreign key. A foreign key is an attribute that appears as an attribute that is not a primary key in one relation and a primary key in another relation. And it must satisfy this referential integrity constraint, which says each foreign key value must match a primary key value in another relation, or the foreign key must be null. Let's look at an example as the best way of understanding it. So we know we have two functional dependencies in sales. Okay, so we have customer ID functionally determines customer name, salesperson, and region, and also that salesperson functionally determines region. But salesperson is not the primary key. So how about this? Why don't we break out the salesperson and region relationship into their own primary key, into their own relation, and call it S-person, as we have there on the right hand side, and let's create salesperson as a primary key. So now we're in 3NF. We have a functional dependency between salesperson and region, and because salesperson is now a determinant and a primary key, we've got no problem. So Smith functionally determines south, Hicks west, Hernandez east, and Falb north. But we still want to keep the relationship between customer ID, customer name, salesperson, and region. So how do we do that? Let's look what it said before. A foreign key is an attribute that appears as a non-primary key attribute in one relation and a primary key attribute in another relation. So salesperson in S-person is a primary key. If I look at sales1, we can see that salesperson is there as a foreign key. We know it's a foreign key by the dotted underline, and therefore we can now connect sales1 relation to S-person relation. So if I look at customer ID of 8023, I know I have customer name Anderson and salesperson Smith. I see salesperson is a foreign key, so let's jump across to S-person. So salesperson Smith is related to region South. So I have the same relationship as I had before. I've now decomposed the relations so that I'm now in 3NF. So how do we transform ER diagrams into relations? Here we have 4 steps. We've got to represent the entities, represent the relationships, normalize the relations, and then merge the relations. Okay, so each regular entity is transformed into relation. That's fine. We get it, right? They're very similar status. They're very similar setups. We have rows, we have columns, we have attributes, we have domains, and so on and so forth. The nomenclature, the naming, God, whoever came up with that word shouldn't have. The naming is different, but the roles are very similar. Okay, so the identifier of the entity type becomes the primary key of the corresponding relation. The value of the primary key must uniquely identify each row in the relation. It's doing exactly the same thing, right? The primary key should be non-redundant, i.e. no attribute in the primary key can be deleted without destroying its unique identification. Fine, yeah, we get it. We're not going to change any of the rules. Okay. Can we represent weak entities? Yes, we can. A composite primary key is composed of the primary key of the entity on which the weak entity depends and the identifier of the weak entity. Okay, so here we would have employee ID and DEP name as the identifier of the weak entity brought across, and we can capture that relationship. Can we represent relationships? Yes, we can. So we've got to think about the degree of the relationship and the cardinalities of the relationship. So remember, the degrees of relationship are going to be unary, binary, and ternary, exactly as we saw in the entity world. And the cardinalities of relationship, we can also capture when we have a one-to-one, a one-to-many, or a many-to-many relationship. And do remember, a many-to-many is always written as M:(n). Don't ask me why. I do not know why, but that's the way that we do it. Okay, so how do we represent a binary to unary one-to-one relationship? So the way we do it, we can either take the primary key of one relation and add it as a foreign key in the other, or vice versa, take the foreign key, the primary key of the other, and put it as a foreign key in the first, or do both. So both primary keys come both foreign keys in each other. So what we've done here is exactly that. So class, I have section number, and then I have room number as building as foreign key, which is the primary key in room. And then in room, I have room number and building as my primary key, and then section number as a foreign key as well. So I've captured a one-to-one relationship in either a binary or a unary relationship. And that's how I do it. If I want to do a one-to-many relationship, I take the primary key of the entity on the one side, in this example, customer, and the primary key of customer ID, and I would add that in as a foreign key in the relation on the many side. So if you can see it order, you can see that I have a customer ID dotted line underneath it, which is the foreign key that ties us between customer and order, customer ID being the primary key in customer. And here we have another example as a result. To do a many-to-many relationship, we have to do something different, and we have to create a separate relation. If you've done the database class, you know this is called a gerund. Okay, in this world we call it also an associated relation. So the primary key of C is a composite key consisting of the primary keys of A and B. Okay, we also include any attributes that are associated with the relationship between A and B, and we would add that into C. So here we have product and order. We would create a new gerund, this associative relation called order line, where the product ID primary key of product and the order number primary key of order becomes the new composite primary key of our gerund order line, which is therefore made up of product ID and order number. Now I've also got ordered quantity because it makes sense in the nature of the relation between product and order to include that attribute. A unary one-to-many. A unary one-to-many relationship, we have to do separate things as well. So we have to have what we call a recursive foreign key. So here we have a relationship between employees within our employee relation. We're basically trying to say that one employee can manage a minimum of 0, a maximum of many employees. An employee can be managed by no more than one employee. I would create a new foreign key that kind of captures the nature of the relationship. In this example, it's manager ID. Now, manager ID should have a dotted line underneath it. That's a typo on my behalf. And it's also going to have exactly the same data as emp ID. All I'm trying to demonstrate is that the manager ID is going to be the employee ID of the employee's manager, essentially. And we call this a recursive foreign key. It references the primary key values of the same relation. So you'll have exactly the same values in manager ID as you'd have in employee ID. What about functional dependencies to relations? So product ID function determines description and room. So product ID would be our primary key and order number as well. And then product ID and order number would be our composite primary key in this example. Merging relations, so this integration of different relations. We're trying to get rid of those relations that we don't need to have. It's the last step in the logical database design, okay? We're doing this before we get to the physical stages. And this is what you had in your 9B assignment. Okay, so we've done all our modeling, we've got everything up. We've got these two relations, employee 1 and employee 2, all right? We think that these is redundant data. We're capturing the same data, but in different relations. Why have two relations? Let's bring them together. So because they have the same primary key and also some other attributes are the same, let's merge them. So employee 1 and employee 2 becomes employee, where we have the primary key of emp ID, and then we just bring across all the different attributes that we need to bring across. So name, address, phone, job code, and tenure. But it's not always that simple, as you probably found in your assignment. Sometimes we have two different names being used for the same attribute. So example, we may have employee number and employee ID when we merge these two relations, and we're actually capturing the same data twice in different attributes. Just get agreement about what it should be called and get rid of one of those attributes. And that's what we call a synonym. A homonym is where a single name is used for two different attributes. So you may have, you've merged two relations and you've got address, you had two, in each of these two relations that you merged, you had an attribute called address in both of them. But actually, when you merged them, you didn't realize that address in one was campus address and address in another was home address. When you create your new merged relation, you need to beforehand rename them as one as home address, one as campus address, and then keep them separate. And this is why I say it's so important that when you're naming your attributes, whether it be at entities or wherever, it's not enough just to have unique names within an entity type, within a relation. All right, you've got to have unique attribute names for every single attribute in the whole of the environment. And that way you can't have the risk of a homonym problem. We can also, as a result of a merger, create a transitive dependency. And this is what we saw in the assignment as well. So here, as a result of merging, we actually create a transitive dependency where our determinant functionally determines our dependent, but our determinant is not our primary key. So here, for instance, we have student 1 and student 2. We see, okay, this is redundant relations. Let's merge them into student. And we have our student ID as our primary key and major and advisor. But as a result of the relations being merged, we've suddenly created a transitive dependency, because we know that for a single given value of a major, there's a single given value of an advisor. This has only come about as a result of the merger. But neither major or advisor are primary keys. So we've taken these two separate relations, we've merged them, we've created a transitive dependency. How do we fix a transitive dependency? Well, we have to decompose. So actually, we're going to create two new relations again. It's a bit of a pain, but we're doing so knowing that we've cleaned up the data even more so than we had done originally. All right. So yes, we're going to still have two relations what we had before, but the relation data is going to be clear. Okay. So what have I done? I've got a foreign key of major in student, which is a primary key of major in this new relation called major advisor. We can also be aware that our class and subclass relationships may become hidden as a result of being merged. And again, I think we saw this in the assignment as well. So we've merged patient 1 and patient 2, thinking that these are the same data, but actually patient 1 was for an outpatient and patient 2 was for an inpatient. And as a result of doing so, we actually lost that difference, that nuances. So how do we fix it? We create class and subclass relations, and therefore we can see exactly that patient, inpatient, outpatient. So patient is our class, inpatient, outpatient are our subclasses. We would take patient ID, name and address, and for our inpatient we'd have room number data, and for date treated for outpatient. And now from the physical side of things, let me just get moving on to my notes. Where are we? We're almost there. Designing fields. The field, the smallest unit of named application data recognized by system software. What else? We've got to choose our data types and data integrity. That's fine. Just look at the notes. Our data types, whatever data type we're going to choose, whether it's CAR, VAR, CAR2, whatever, so on and so forth. We're doing so, making that decision based on the available space to store data and the speed with which we need to access that data. So when we're making this decision, we're basing this on keeping our storage space to a minimum, having all the possible values that we need to have, maintaining the data integrity of our field, and all the different data manipulations, the insert, the updates, deletes, and so on and so forth. We can manage that as well. All the time, we're trying to make sure, maintain our environment so that the maintenance updates are reduced to what we can absolutely need and nothing more. What other data integrity controls can we have? We can have default values. We can put our range control, our domain, our property value set. We can say we have this referential integrity. Okay, we see a referential integrity constraint in relation to our foreign keys. So this is a constraint that specifies that the value existence of an attribute in one relation depends on the value existence of the same attribute in another relationship. In another relation, that's our foreign keys, and then a null value. Okay, we say whether we allow null values or not. So when we're designing our physical tables, remember the difference between a table, a relation, and an entity type. So a relational database, a set of tables that are related by foreign keys referencing primary keys. Do remember that a relation may not, and probably will not, neatly correspond to a physical table. Our aims of our physical tables are different to our aims of our logical relations, right? So our aim of a physical database table is to be as efficient and effective as we possibly can, right? We want to be fast. We want to be able to access our data quickly and get out as quickly as we possibly can. Now, we also perhaps have to go through this denormalization process as well. All right, so we've got our really nice logical normalized data. We've made sure we got rid of all our redundant data within a relation. We've got rid of our redundant relations as well. We've dealt with all our synonyms and homonyms and all that good stuff. And now we're going to blow it all apart and move data around, predicated on where it makes sense for data to be physically close together. Maybe it's because one department only has to access one bit of data, so let's put all their data together. Another department has to access only their data, let's put all their data together, and so on and so forth. We can also partition tables. So we can split a table into separate sections, either on range partitioning, hash partitioning, or composite partitioning. And each partition is stored in a separate contiguous section of disk space, i.e. next to each other. So what are the trade-offs of denormalization? Well, we can actually go through this denormalization process, increase the chance of errors and inconsistencies, but we're doing so based on our recognition that we need to be as fast, which we're basically trying to get the best of all worlds, right? We want to have the cleanest data as we can, but we also want to be as fast as we can as well. All right, so it's a balance, and not one situation is going to be right for all other situations. It's a best effort approach for getting the best of all worlds. Okay, so if you have two entities with a one-to-one relationship or an associative entity, all right, with a many-to-many relationship, i.e. a gerund, then that might be a common situation for denormalization, or whether you have data that is reference data. Okay, what else do we have? Ranging table rows. So we have physical file, a name set of table rows, all stored next to each other. A pointer, the field of data that can be used to locate a related field or row of data. What other common file organizations do we have? So we can have sequential rows, index rows, or hash rows. Look at the slides to get examples of that. And what about controls for our physical database? Well, we do backups, and we can put security controls in place as well. Woo! Right, so there you go. Along with the practice exam and the PDFs of this video, hopefully you're going to be in as good a place as you can be to do well in the exam. If you've got any questions in the meantime, please do reach out to me. I'll be very happy to help you. In the meantime, good luck, and hopefully all will go well on Wednesday's exam. Until then, see you later. Take care. Goodbye.